hello to all my young friends who are studying in intermediate and they are watching this video. My name is Salman and very recently I created this online platform. Today we are going to discuss a very important topic from physics, and the name of the topic is relative velocity. Relative velocity right now is taught in the initial chapters of physics. Earlier it used to be taught uh, in mathematics, and it used to be a part of mathematics and under the chapter of dynamics, but now it has been made a part of physics and it's taught in the initial chapters. So let us know about relative velocity. What is relative velocity? Many people find relative velocity a bit complex, and the problem related to this relative velocity, they find it difficult because the motion of 2-3 different objects is involved, and that too in different directions. It makes things a bit complex, but if we stick to basics and if we know the basic principle how to solve these problems, and if we have a basic concept of relative velocity, then we can simplify all the problems and they can be solved very easily. So it is imperative that we have a proper concept of relative velocity. So what is relative velocity? For example, let there be two bodies A and B moving in different directions with different velocities as shown. This is A and this is B, and they are moving like this: VA velocity and VB velocity. Now the velocity of an object A related to another object B, velocity of A relative to another object B, it is denoted as VAB. This means velocity of A relative to B. It is the velocity that object A would appear to have to an observer moving with B. Suppose there is an observer here who is moving with B, and he is seeing object A. So how will the object A appear to this person who is moving with B? That is VAB, that is velocity of A relative to B. Now the question is how to calculate the relative velocity. Let's consider two cases, in fact two simple cases in the coming slide. Case 1. Let there be two cars A and B moving in opposite direction. A is moving with 40 km per hour in one direction and B with 50 km per hour in other direction. They both are approaching each other on the same road. So you can just pause the video and think, how will B appear to a person sitting in A? Definitely you must have guessed it right, that B will appear to come with higher speed. So car B will appear moving faster than its actual speed, and the velocity of B will be 50 plus 40, that is 90 km per hour to an observer who is in car A, because car A is also moving towards B. So VBA, velocity of B relative to A, is equal to 90 km per hour. Now how did we find it? What did we do? We took the velocity of B, this is VB, is equal to 50 kilometer per hour, and we reverse the velocity of A and add it to that. That means we added VA here, which is equal to 40 kilometer per hour, and we got this as 90 kilometer per hour. What does that mean? That means we reverse the velocity of B, reverse the velocity of A, and add it with that of B. Hence, velocity of B relative to A is equal to VB minus VA. Right. Consider another case. Now the cars are moving in the same direction. This with velocity of 40 km per hour and this with velocity of 60 km per hour. Now car B will appear moving slower than its actual speed. It is moving with 60, but a person who is sitting in car A, since car A is also moving at 40, to that person car B will appear to move with a speed of 60 minus 40, that is 20 km per hour. Now what did we do? We did the same thing. VBA, velocity of B relative to A, is equal to VB minus VA. So what we did, we reverse the velocity of A and add it to B. Now B is 60, and A direction is this, but when you reverse the direction it will be 40 in this direction. So the resultant will be 20 in this direction, 20 km per hour. So again we reverse the velocity of A and add it to B. So now these cases are very simple because they are in the same line. Hence we added and subtracted algebraically. However, the general rule is that they are done vectorially. Suppose in both the cases, in one case this was the direction of A and this was the direction of B. In another case this was the direction of A and this was the direction of B. So they were in the same line. So you could add or subtract them algebraically. But if the directions are different, suppose A is in this direction and B say is in this direction, then what to do? We'll use the same rule, but here addition and subtraction will be done vectorially, not algebraically. So VAB, velocity of A relative to B, is equal to VA minus VB, where VA is the velocity of A, VB is the velocity of B. So you have to remember this equation. This is the basic equation of a relative velocity. So for calculating VAB, we will vectorially subtract VB from VA. Now you must be knowing how to subtract one vector from another vector, but again I'll just touch that topic also. Suppose this is vector A and this is vector B. Now if you want to get a difference of A vector minus B vector, how to find it? Take this A vector and add B like this, multiply B by minus, so its direction will change. So this vector is going to be A minus B vector. I hope you are clear with this right now. Now let's consider few examples in the coming slide. Suppose this is a train which is moving in this direction as shown, and there is a tree. Now to a person who is sitting inside train, the tree will appear to move in this direction as shown by this green arrow. VTP means velocity of tree relative to person. Suppose there are two trains, train A and train B. Train A is traveling with a velocity of VA in this direction, train B with a velocity of VB in this direction. Now you all must have experienced that when this kind of situation happens, that another train comes on the adjacent track from opposite direction, it appears to go very fast. Now to a person in train A, train B will move with higher speed. That means if this arrow depicts the magnitude of speed, so the train B will appear to move with a much higher speed. Velocity of B relative to A, right? Now if there are two cars, car A and car B, and they are moving with speed VA and VB in the same direction, if VA is equal to VB, then to a passenger in car A, car B will appear to be stationary or move with, say, zero velocity. Similarly, for a person in car B, the same thing. Suppose this is a car which is traveling with velocity of VC in this direction, and rain is falling with velocity, say, VR, vertically downwards. But we all must have experienced that the rain, although it is falling vertically, but it appears to fall inclined at an angle with horizontal, say with velocity. RC means velocity of rain relative to car. For example, this is a person who is going vertically upwards in a balloon, VP, and there is a train which is flying like this with a velocity of VC. Now my question is, how will a crane which is flying in horizontal direction appear to this person who is ascending vertically upwards? Or if a jet A is going in this direction with a speed VA and another jet VB with a speed VB, my question is, how will the jet B appear to the pilot of jet A if they are moving in the same plane? Because here we are concerned with relative velocity in two dimensions. Take the case of a space. There are two spaceships, VA and VB. Both are moving in the same plane. Now, question is, how will the spaceship B appear to move to an astronaut who is in spaceship A if both spaceships are moving in the same plane? Now let's revisit our earlier slides and get the answer to our question by applying concept of relative velocity, right? Now what is the concept of relative velocity? Simple. Velocity of A relative to B means VAB is equal to VA minus VB. You just remember this equation, that is the key to solve all questions on relative velocity, and very, very important result. Now, this is the first example which I gave. We know that the tree is stationary, but to a person who is moving in train with a velocity of say Vp, we call it velocity of person. The tree, velocity of the tree relative to person will be velocity of tree minus velocity of person, right? Now velocity of tree is 0, so Vtp is minus Vp, means the tree will appear to move with the same velocity with which a person is moving, but in opposite direction. Because person is moving in this direction, the tree will appear to move in this direction, right? So this is how we got it vectorially, VTP. Now the second example, where train A was moving in this direction and train B was moving in this direction. So to a passenger in train A, B will appear to move with higher speed. VBA, velocity of B relative to A, is VB minus VA. So what we have to do, we'll take VB and we'll multiply VA by a minus 1 and we'll add it here. That is minus VA. So this will be the magnitude of VBA, velocity of B relative to A. So you can just imagine, I'll take this vector and put it here. So you can see this is VBA, velocity of B relative to A. So this arrow represented the speed of B, but now just see, this arrow is much bigger, that the speed is much higher. Now these two cars are moving in the same direction, so relative velocity VBA, velocity of B relative to A is VB minus VA, which is equal to 0. How? We took this B vector and A vector in a negative direction, so they both cancel out and become 0. Example of car, velocity of rain relative to car is equal to velocity of rain minus velocity of car. So we'll just take the velocity of rain and add minus Vc, that is minus velocity of car, and we'll get velocity of rain relative to car. So rain will appear to come like this, which we are showing in green color, inclined and certain angle. Now this arrow represents the magnitude of velocity of rain, but this arrow represents the magnitude of rain velocity which appears to the person sitting inside a car. So you can see the magnitude is also more. So rain appears to coming with a higher speed. Now you must have noticed that if you increase the speed of car, the rain appears to come even with more velocity. Many of you must have experienced this. Now coming to these three questions which we had asked. Velocity of crane relative to person is velocity of crane minus velocity of person. So we have reversed the velocity of person and added to VC, velocity of crane. So this is the velocity of crane relative to person. So this green arrow I am showing, this is the direction and velocity of crane which will appear to this person who is ascending upwards. Now coming to an example of jet, velocity of V relative to A means velocity of jet relative to the pilot of A is VB minus VA. So this is VB and this is minus VA. So this is VBA. That means velocity of B relative to A. So I'll put the arrow here. So this is the velocity of B relative to A. That means this red arrow shows the magnitude and direction of B, which will appear to pilot of jet A. Coming to the example of spacecraft, velocity of B relative to A is VB minus VA. This is VB minus VA, VBA, velocity of B relative to A. So this yellow arrow shows the magnitude and direction of spaceship B, which will appear to a person or an astronaut in spaceship A. I hope these examples must have cleared your concept of relative velocity. Now I'll also discuss one or two more important concepts here. Now we already have seen that if AB is the velocity of A relative to B, then VAB is equal to VA minus VB. So we are adding the negative velocity of the observer to the velocity of object which is being observed in order to get the relative velocity, right? However, one important thing which some of you must have read, this implies that observer is made stationary. At times people ask, how is it possible that observer is stationary? I'll just explain you with an example. Say, let's understand how observer is made stationary. Suppose there are two objects, or you can say person, who are right now in these places, standing and facing each other, A and B, two persons. Now if A is given a velocity V in this direction and B is also given the velocity of V in the same direction, so the picture will not change, right? They will be, in the same position. The distance between them will be same, because if A is moving with velocity V in one direction, B is also moving. That means if one is adding velocity in any direction, the same has to be copied by other, so that the picture does not change. Let's see few examples. Say if these are A and B, if A is giving, then B also is given the velocity in the same direction, picture will not change. A is given velocity in this direction, B in this direction, again picture will not change. If A in this direction shown by purple color arrow, B also the same velocity, picture will not change. Hence adding the same velocities to both does not alter the picture. Okay, I think you understood this. Now consider two objects A and B moving with different velocities in different direction, like A is moving with velocity VA and B is moving with velocity VB. Now what we have said, if we give one velocity to one in one direction, the same has to be copied to other, so that picture does not change. Now what we'll do, we will add minus VB to both, which we can do, so that picture should not change. So minus VB, minus VB. But here, now when we have added minus VB here, it will become VAB, velocity of A relative to B. That means B is observer, and for VB, this will become 0, because VB in one direction minus VB in this direction. So that is how observer becomes is stationary. The other important concept is distance of closest approach. If two objects are moving in different direction, so how close then can they come to each other? That is called distance of closest approach. Before I discuss that topic, let me recall something from geometry, elementary geometry. You must have read that of all the line segments that can be drawn from a point to a line not containing it, the perpendicular line segment is the shortest. That means if this is a point P and this is the line, now of all line segments that can be drawn like this, these are all, the perpendicular is the shortest. I think you all must have read this in geometry and must have recalled this. So this is the shortest. And this is what we call distance of a point from a line. Actually, it is a perpendicular distance. Now, what we'll do, the closest distance of an observer from an object traveling in a straight line, not passing through observer, is the perpendicular distance on the trajectory of the moving object. Like for example, if this is a stationary observer and A is moving with VA velocity in this direction, that means this is blue color is the trajectory of A. So how much close can A come to this stationary observer will be if you draw perpendicular from this point on this trajectory. This is going to be the shortest distance or distance of closest approach, right? Now, if two objects which are x distance apart, one is moving with a velocity of v in this direction, another moving with velocity vb in this direction, they are x distance apart, and we want to ascertain how close can they come. So make one as observer, either A or B. Suppose you make A as observer, so that means A is stationary. Calculate V, velocity of B relative to A, and then that means B will appear to move with this velocity to stationary observer A, and in this direction drop a perpendicular from A. I'll just show you how. Calculate VBA, that means this is VBA, this is the velocity of B relative to A, that means A is stationary. So you drop a perpendicular from A on this trajectory. This is AC is the distance of closest approach, and what will be the time required? Suppose B and A are in this position right now. What will be the time required when they come closest? That time is this distance BC upon VBA, right? So that time is BC divided by VBA. I think you must have got a fair idea of both these very, very important concepts. Now, when we solve the problems of relative velocity, we can use one or two very common methods. One is we can solve them using basic geometry, or we can also take the help of orthogonal unit vectors, in this case I and j. At times this makes the problem very easy, but at times it is not required, it may not be required. You can solve it easily by basic geometry. So that's up to you. Once you start doing the questions, get a fair idea, then you can choose either of this method, the best suited method. That's up to you. So let's consider an example for employing both the methods. I'll consider an example where I'll solve the question by both this method. First, by using basic geometry. Second, by using orthogonal unit vectors. In fact, orthogonal unit vectors at times make the problem very easy. The question says the cyclist is going on a horizontal road with a velocity of 5 meter per second and it is raining vertically downwards with a velocity of 4 meter per second. Now, at what angle should he hold the umbrella to the vertical so as to protect himself from the rain? Now, rain is falling vertically like this. Had my cyclist been stationary, he would have to hold umbrella like this because rain will appear falling vertically only. But since cyclist is also moving in this direction, rain will appear to fall inclined at an angle or some angle, say theta, with horizontal, what we saw in the case of car. So what we have to do, we have to calculate velocity of rain with respect to cyclist. That will be velocity of rain minus velocity of cyclist. And we will get the direction of velocity of rain relative to cyclist. And this is the direction in which the cyclist has to hold his umbrella so as to protect himself from rain. Just see how we solve it. The first method is geometrical. This is velocity of cyclist and this is velocity of rain. Now, velocity of rain minus velocity of cyclist. This is, we have reversed the direction because we have to calculate velocity of rain relative to cyclist is equal to velocity of rain minus velocity of cyclist. So this will be velocity of rain relative to cyclist. Now what he is asking, at what angle should he hold umbrella to the vertical so as to protect himself from the rain? So this is the angle, say this is theta. So tan theta is equal to, this side is 5 and this side is 4, is equal to 5 by 4. So theta is equal to tan inverse 5 by 4. That means this theta is in this direction to vertical, that means clockwise direction. So he has to hold umbrella like this. And this is the answer, tan inverse 5 by 4 in clockwise direction. This is a pretty simple problem, and we got the answer through geometrical method. Other problems also, if you go by the basics, they are quite easy. In some problems, you have to spend a little more time, but if you know the concept, you can easily solve them. Let's do the same thing by orthogonal unit vector method, method 2. Now, here you are at your liberty to choose the direction of orthogonal vector. Say, if you can take I like this, and you can take j like this, or you can take I like this, you can take j like this. So that's up to you. Now, for example, if I take I like this and j like this, then VC is equal to how much? 5I, because I direction is this one, and VC direction is also the same. And VR, velocity of rain, is equal to, it is in reverse direction of J, minus 4J. That means velocity of rain relative to cyclist is equal to velocity of rain minus velocity of cyclist is equal to minus 4J minus 5I. We can write in order: minus 5I minus 4J. Okay. This is your VRC. We generally write this cap. Minus 5I minus 4J. Now, VRC is equal to minus 5I minus 4J. So what you should do, just again make Ij, and minus 5I minus 4J is that you have to go in the negative direction of I, 5 units, and in the negative direction of J, 4 units. So this is your VRC. Now he was asking about this angle theta. So this if this angle is theta, then this angle is also theta. So you can easily see tan theta is equal to 5 by 4. Theta is equal to tan inverse 5 by 4. Pretty simple. Now here only direction of relative velocity is being asked. If they ask magnitude, VRC magnitude will be under root 5 square plus 4 square, which is under root 25 plus 16, whatever it is, right? So this is solving relative velocity problem by two methods. Both have their own advantages, and in fact at some time disadvantage also. One process may be, a ship A is moving westwards with a speed of 10 km per hour, and another ship B, which is 100 km south of A, is moving northwards with a speed of 10 km per hour. The time after which the distance between them becomes shortest. That means this is a problem on distance of closest approach. So first of all, let's draw the directions: north, south, east, west, and A is moving with 10 km per hour, and in the direction of west. B is 100 km south of A, and it is moving northwards with a velocity of 10 km per hour. Now you have to find what is the time after which the distance between them will become shortest. So in this case, you have to make one as observer and move other with relative velocity, and on that trajectory you drop a perpendicular from the observer, and then you can calculate the shortest distance and the time required. So we'll make it a bigger figure so that it doesn't become cluttered. This is A, and distance between them is 100 VA, VB. Now what if you make B as observer? So A will move with velocity of A relative to B, which will be velocity of A minus velocity of B, right? So what you have to do, reverse the velocity of B and add here. So A will appear to move with this velocity VAB. Now since this is stationary, so you have to extend this trajectory, which A will appear to move and on this trajectory you have to drop a perpendicular from B, and then you have to calculate the shortest distance and the time required for that. So we'll do that. We extended this red line, and we dropped a perpendicular from B, say C. Now time required will be AC upon VAB, and this BC, this is the shortest distance, right? So you have to calculate AC and VAB in order to get the time. So what we'll do, first of all, we'll calculate VAB, because here I'll write T, or time, AC upon VAB. Now VAB is equal to, this angle is 90, this side is 10, and this side is also 10, is equal to under root 10 square plus 10 square is equal to 10 root 2. VAB is 10 root 2. And how much is AC? Now this angle and this angle both are 45, because this side is 10, this side is 10, so this angle also will be 45. So we know AB, so AB upon AC is equal to how much? Sec 45 degree, right? And sec 45 is under root 2. AC is equal to AB upon under root 2, which is equal to, AB is 100 upon root 2. So now our time is AC upon VAB. So time is equal to AC, that means 100 upon root 2, this whole upon VAB, 10 root 2, which equals to 100 upon 20 is equal to 5 hours. Let's check the answer. The answer is 5 hours. I hope you had understood the concept of relative velocity, and these problems make it more clear, and I hope that you will be able to solve the questions from your book easily right now. Just go and try out some questions from your book to get an in-depth understanding on this topic. If you do more and more questions on this topic, you will get more insight into this subject. And this topic, that is relative velocity, is one of the favorite topics of especially examiners of competitive exams. So please pay proper attention to this. So I hope you enjoyed this video, and the concept of relative velocity is clear to you. Thanks for watching this video. Have a nice day.